the uh, the first thing. Now, just don't get into the flow of this document, okay? I will start speaking and I will start explaining the process, whole process. When the contract is awarded, or we are starting the engineering, either phase 3 or phase 4, okay? So the very first thing what starts is basically at site. If you talk to me at site, there is a pre-engineering survey is carried out by the feed consultant or the contractor. Okay, so I will not repeat now every time feed consultant or contractor. You consider both of them together. So what we do first is we start our engineering survey. Okay, so the engineering survey is the first activity. It is written in the heading of piping, no doubt in that. But the team of all the engineers, okay, they take part into this pre-engineering survey. They try to gather all the information as available information from the site. That is point number one. So that means they may they may be having some missing information. Okay, but all these things required to be validated during the site survey. And after the site survey, uh, there will be a recommendation in that site survey report. There will be an observation report in the site survey report, what they observed exactly. For example, they will do a plot plan survey of 300 by 300 plot plan survey by the given coordinates. And the contractor will say, sir, when we did the survey at site, we found 2 extra facilities there at the site survey. So it required to be dealt accordingly. So that's why the pre-engineering survey is one of the mandatory activity, and there is a report also mandatory, and which becomes the basis for everybody. So that is point number one document. Similarly, all the disciplines, they will develop their design basis documents. Okay, if you see here, all civil design basis, electrical design basis, instrumentation design basis, mechanical design basis. This is nothing but basically the design concept, how the engineering will flow from each perspective or from each of the discipline point of view. What will be the pressure conditions, what will be the temperature conditions, what will be the compressor configuration philosophies, what type of compressors will be there, what kind of instrumentation systems will be there based on codes and standards. Our gas mitigation project scope of work covers some portion of this design basis also. Okay, so this design basis is nothing but it makes sure that whenever you are developing further documents, it includes the codes, standards, design selection philosophies, everything, correct? So this is the design basis document for each discipline. So we have done with the pre-engineering survey, we have done with the design basis. Now we'll see, uh, okay, now we'll see the discipline by discipline, okay? That will be the basic how the documents flow. In the process, there will be a process flow diagram with heat and mass balance will be created. Uh, Basically, this is essentially required to know what is our throughput or what we are handling, how much we are handling, and what will be the distribution of that. Suppose we are handling gas, or we are producing gas, or we are producing well fluid. So at the subcenter, forget gas mitigation project right now. When you are at the subcenter, you are going to handle total fluid of 100,000 barrels. In that, how much will be the gas? How much will be water? How much will be oil? And where they will be going it? What will be the material balance? What pressure and temperature conditions will be there for production? So that becomes a first driver for starting the total overall process design of the plant, particular plant. So that's why this is a process flow diagram, and heat and mass balance is essentially required to know which stream is going where. A stream, when I'm telling, means oil, water, and gas. So which stream is going where, how the streams are together, where they are separated, what is the load conditions occurring, like this. Then after the process flow diagram is developed, there is one more report called, we don't have it I think in gas mitigation project, but corrosion allowance calculation and material selection. There is a report actually. Okay. This report sometime is developed by process engineer or with the support of metallurgy engineer also, because you will have to calculate the corrosion allowances pressure and temperature condition. Not it's only the fluid property, whether it is sour or it is sweet. No, not only that. Sometimes when the temperature increases, if we are dealing with the high pressure temperature condition, specifically for the compressor discharge line, The small ppm of H2SO2 is more corrosive at high temperature condition. So that's why the metallurgy selection has to be done, and for that there is a calculation for corrosion rounds and intermaterial selection conditions. P&ID, piping and instrumentation diagram, we all know that is developed, and this piping and instrumentation diagram, which is a non-scale document, point number 1, but it tells you everything. It will tell you how many vessels are coming, how the fluid is flowing basically. So it's basically in to out of that plant. What will be the controls it will be having? What will be the pressure conditions will be there? What will be the temperature conditions will be there? What is the how much piping? Sorry, not how much. I'll say what piping ratings will be there for that temperature conditions. Correct. In this scenario, we will be knowing the major equipment capacity. For example, separator. So you will know this. What is the separator capacity? What is the retention time? But you will not know the piping length and all. Okay. So in P&ID, you know the piping connecting one separator to one tank, but you will not know what is the length of that piping in that. Okay. You will know dia, you will know service application, but not the length. Correct. So that length will come in the next documents. It will come. Correct. So that is called the P&ID, what we are having it. Okay, we are all very familiar with it. Then it is coming process data sheets. The process data sheets will be developed for each and every equipment available in that P&ID. If you have header, there is a process data sheet for header. If there is a separator, there is a process data sheet for separator. If there is a pump, there is a process data sheet for pump. There is a temperature sensing, there is a level sensing, there is a control valve. There is a process data sheet for that also. So, in nutshell, we can say for mechanical equipment, whether it is rotary, like a compressor. Second mechanical equipment is static. That means like a separator, tanks, correct? They are static equipment for that. Similarly, instruments, okay? Flow meters, controls, correct? All. So all these things will be having a process data sheet essentially required. Because based on that process data sheet, respective teams will decide, or they will select, they will develop their own data sheet. Like when you develop the process data sheet for compressor, the mechanical engineer will take your process data sheet and he will develop mechanical data sheet based on your process data sheet for his compressors. By the way, mechanical data sheet will be completely a different format. What kind of compressor, what kind of drive, electrical drive or gas drive, centrifugal compressor, how many stages. That will cover purely about compressors. Okay, but the basic input will be from process data sheets. Okay, then so this is because this is the start point for all the disciplines. We have to understand this point. This is one of the great start point for all procurements. Sorry, for all the data sheets by the different disciplines. So this is one of the critical documents. Then it's coming to the HAZOP report, as we know that. Okay, we all have discussed HAZOP also in the past also. But the HAZOP concept is when you are doing HAZOP, you are looking for any hazards in operations, correct? But when you are looking for hazards in operation, the basic assumption is that all the designs, these documents are frozen. That means the engineers have done their job very well. The design is completed. P&IDs are approved. Process data sheets are approved. Everything is done. Okay. And then you are conducting a HAZOP for that. Okay. So when you do HAZOP, that means you are doing on the best document available with you. You are doing on the P&ID basically. The basic required document is P&ID. You do HAZOP on P&ID. So P&IDs are approved already. Correct. So that is a concept. But then still you may find some flaw with hazards from operatory point of view. So that changes has to be done in P&ID, and in turn it is reflected in the equipment data sheets. Either it is instrumentation equipment, suppose you have to put some extra control valve, you have to put some extra safety valve, or you have to put some block and bleed valve, whatever you want to put it there. Okay, so that will be HAZOP report may add something extra from the hazards point of view to safeguard the hazards basically. So this was the broadly the process scenario. Then I will come to the piping. Okay, already these two documents, piping design basis and pre-engineering survey, we have discussed. Okay, now coming back to the plot plan. So the very first thing which will be developed after the survey and all will be, and the basic equipment list when we know what is should be there in the plant. the plot plan is developed. Uh, the plot plan is developed based on the bill of quantities, what we are going to have in our plan, everything, what are the main equipments, areas we are going to have it. While developing the plot plan, basically, when we'll review the plot plan, we'll understand that in more detail, but basic idea is like you cannot make your office next to the compressor area, okay? Because we try to segregate between the hazardous and non-hazardous areas. You cannot have your office near to your flare. You have to maintain some safe distances, correct? So the plot plan is developed based on safe, unsafe areas, hazardous areas, non-hazardous areas, basically. Okay, this is basic guideline for plot plan. There are standards available for that. That you have to maintain this much distance from flare. You have to maintain this much distance from compressor plant. This much distance should be there for control room from the flare. All those details will be there, correct? So basically, the plot plan is developed, correct? Now, after plot plan is developed, then it comes to the equipment layout. See, in the plot plan, what you do, you highlight compressor area as a one box, okay? Say, in the total footprint of 300 by 300 meter, your compressor area is maybe 25 meter by 25 meter box in the plot plan. Now, in equipment layout, now you develop that those individual blocks in detail. Now you'll be developing another equipment layout for compressor area. So that 25 meter by 25 meter, in that you'll be showing that you are putting 3 compressors there, correct? So this is how the equipment layout works about. Okay, so you go into the blocks now, individual blocks of the plot plan. After this, once you have done that equipment layout, this equipment layout helps a lot to the piping engineer more, because when you put a compressor, correct? So example, when you are putting a compressor, so you are putting your compressor northwest or something like that, in some directions like this, correct? So in that scenario, you fix that from where the gas is getting inside the equipment, from where the gas is coming out of the equipment. So based on this compressor location, equipment layout of compressor, the piping engineer will further design his piping layout, that he has to put the inlet piping and outlet piping. So this is how the next step will be. Once your equipment directions, orientations are frozen, then it will help us to start generating the piping layout of the plant. Okay, that's the advantage of equipment layout. The next document from equipment layout, basically. Hazardous area classification drawing again. Yes, there is a standard to develop hazardous area classification drawing. It is like, for example, closed system, open system, okay, hazardous system, non-hazardous system, okay. So based on that, the hazardous area classification drawings are developed, and the most important hazardous area classification drawing is why it is essentially required, because whatever the instruments, whether it's electrical instruments or the instrumentation control items, whenever you are putting them in hazardous area, the equipment should be I'm sorry, the equipment should be usable in hazardous area. They should be explosion proof, flame proof. Sorry. So it should be like fail safe, or sorry, not fail safe, explosion proof, flame proof, and one is called weather proof, correct? So suppose if there is a light which is at our gate of the plant, and that is in safe area, not in the hazardous area. So it need not to be explosion proof light, okay? Okay. It can be weatherproof is sufficient. What is weatherproof? It should be protected from water and dust, IP, okay? But suppose the same light, if it is coming inside the compressor shade, then in that scenario, it will be explosion proof and flame proof. That means if anything happen inside that light, that spark should not go outside. And the second thing, if some leakage happen outside gas, that gas should not go inside the light. So this is basically the concept of hazardous area equipment protection. Not only for light, for instruments also, pressure transmitter, temperature transmitter, all these things, correct. So this is about the hazardous area drawings. Okay. Now purely about the piping mechanism. Stress analysis report for flexibility, dynamic, seismic analysis, planned leakage analysis. What happens when we are putting now we are coming to piping correction. Say for example, the compressor outlet is going to the main 18-inch pipeline, correct? So in that pipe portion, we will do a stress analysis. We'll do a flexibility analysis also. I'll get into the details of this in a separate section, okay? But the basic concept of all these reports is that when the compressor is running, okay, and there are vibration on the compressor skid, correct? At same time, suppose any earthquake comes. So forget earthquake, I talk earthquake separately. So when the compressor vibrations are transmitted to that pipe, correct? So that pipe should not break. The welding joint should not break. The flange joint should not break, correct? And it should have a sufficient flexibility. See, you cannot stop the compressor vibration to transmit on the piping. That is next to impossible. So the vibration will be there. But your piping system should be in such a situation that it should be able to address the vibrations which are coming. Of course, the compressor vibration should not go beyond certain limit. That condition monitoring system will be handled separately. Like the compressor should not vibrate unnecessarily beyond the designed limit of vibrations, okay? But within the design limit of compressor vibrations, whatever vibrations are getting transmitted to piping, inlet piping, outlet piping, that piping should not crack, okay? The flanges should not crack, okay? The joint should not snap, okay? So all these studies are done about the piping system. This is one of the critical analysis because safety has been secondary. So this is what is being studied here about this. And in this also, when we are analyzing the observations about the compressor rotary equipment, air compressor, gas compressor, pump also, in case of pumps also, correct? So in that scenario, one more load is considered, which is called the seismic load. Okay, or the when the pipe is put on the pipe rack, correct, hanging, okay, or if suppose at that time, suppose if the compressor is running, suddenly earthquake comes, so it will add an extra stress on the compressor and pipe joint, correct, and pipe. So in that scenario also, that seismic analysis will tell you it is good to go. It is already, you have considered extra supports for that piping, you have considered shock absorber in between, you have considered the joints, flexible joints in a way, if the vibrations are more, that will address it. So all these things will help you to analyze that your compressor and piping relationship remains smooth without any trouble for lifetime, design life of 20 years or 25 years. So this is what the stress analysis reports and all these things are mandated to do. Okay, then piping underground facilities layout. If there are some underground facilities that need to be identified very clearly, whether it is existing or the new pipelines or new facilities are coming, so that will be a layout for the generally closed blowdowns. All those things are coming up in our cases where underground facility is where the liquid has to naturally go into from the vessel. It has to naturally go and get collected in an underground sump. Okay, so it will get collected there. Piping general arrangement drawing. Okay, so how the piping will be, so general arrangement drawing of piping, okay? How the pipe will be traveling on the rack, or the pipe will be traveling on the local supports, or pipe will be hanging in air for a couple of distances. So this is basically anything but total piping general arrangement inside the plant, okay? Then coming the nozzle orientation drawings, okay? Nozzle orientation drawing is, it has a two component basically. The process, I'm going back to process, okay? The process will tell you on the vessel how much nozzles will be there. I'm making it very clear. If there is a separator, in that separator, if the inlet connection is of 6 inch, which is called nozzle, okay? You are connecting through nozzle, okay? Nozzle and flange, okay? But this 6 inch size will be decided by process, okay? And at which angle it will be there. From the base, it will be at 2 meter height, and it will be at the 180-degree angle or 250-degree angle. That will be told by, basically that will be told by the process, okay? Because that is a part of the design of that particular vessel, or the compressor manufacturer is giving with their nozzle connections, correct? So based on that nozzle connections, the nozzle orientation drawing, because you have to connect the piping to that nozzle, correct? Hookups basically. So then the piping engineer will design orientation drawing for that nozzle, that okay, this nozzle is there, and for this my piping orientation will be like this. My pipe will first go 180-degree, then it will take a 90-degree bend, something to come back to the main piping rack, correct? So that is called nozzle orientation drawings. Then piping isometrics, okay, and we know that the isometric drawings are required for the construction of piping. But finally, this is almost the end result, which is the construction engineer at site and the contractor. They use this document to fabricate the final spool piece of piping based on this isometric drawing. Basically, they are the approved for construction kind of work. Piping support and pipe rack layout drawings. Yes, we know how many pipe supports will be there, what will be the pipe rack will be there. Okay, so yeah, that will be there. Hazard report. Basically, as we said, HAZOP report is based on P&ID. So the hazard report is based on the plot plan actually. We perform hazard on plot plan. So we make sure that our safe distances are maintained. Wind direction, suppose if there is a wind direction, correct? The wind direction is also taken into consideration. Suppose if there is a gas leak, so the gas leak should not happen that if there is a gas leak and wind is normal. 80% time wind flows in one direction in a year, correct? So that wind normally should not take that gas to a flare area or any area which is like a flame area, correct? So that we'll study in the hazard report. This basically based on the plot plan, okay? Piping hookup index, yes, where are we are going to hook up our pipes, because when the pipe is traveling on the racks, but there will be hookup index, this pipe is getting hooked up to separator and this pipe is getting connected to this, so it's basically an Excel table kind of thing. Okay, so that's a hookup index, another document used for the construction site. Basically a summary of the hookups. 3D model, yes, the whole plant basically developed in the 3D model, showing the connection of the piping with the vessels and everything. Okay, and so this nowadays is very 3D model is a very common phenomenon which is used to visualize the piping connection, and at the same time it gives you three-dimensional look of your plant. Okay, so you come to know whether the clash is happening, two pipes are crossing each other, or there is not a sufficient space between two piping, or there is a not sufficient places available between the vessel and the piping so that a man can pass through that. If it is some maintenance activities are there and everything is there, so it's basically nothing but it's a three-dimensional views created for the plant, wherein we are clearly visible. You can walk through, basically so walk through to the plant. Okay, that how the plant will be there, and that helps you out to understand how the layouts will be, correct? Okay, and how now I go back to I'll be a little fast. I'm going fast, but so just catch it. The recording is happening. And then I'm going to civil, as I said, civil design basis we already discussed. Now coming to the benchmark. Okay, uh, the benchmark is basically when we are constructing a plant. This point should be known, that when we are making a plant, correct? So from where it should start, like at what height my office building should be there from the ground, present ground level, at what level my compressor should be there, at what level my water tank should be there, water pump should be there, correct? So for this we transfer the ground level and we put a benchmark there. Okay, the level of this ground at this location is 160 meter from mean sea level. Okay, and we put a benchmark in our plot. Okay, now from this benchmark, which is for example Wafra is at 160 meter mean sea level. Okay, Meena Ahmadi is at almost 5 meter mean sea level. Okay, so our plot is say 160 170 meters mean sea level. Now you will say, okay, my compressor will be, now what you do, when you put a benchmark there at 160 meter mean level, now from that benchmark you will decide your all the foundation. Okay, my compressor will be 2 meter above it. So now the foundation, top of the foundation for my compressor will be 162 meters. Okay, so like this. So the purpose of benchmark is defining the level of that particular plot clearly on so maybe 1 feet block you put, and on the top of that you put a metal plate, and on that you say that it is 160 meters. Okay? So that is called the benchmark document. Start point for civil work. Then it is coming to general arrangement layouts for finished level. As I told that now we'll decide that compressor will be at 162 meter height, or what sometime what they do. Sometimes what they do, that 160 meter benchmark what we have been put there, they will consider that in the civil drawing as a 0 level. So for this plot, that is a 0 level. So now compressor will be plus 2 meters. Civil building will be plus 3 meter from that 0 level benchmark. Okay. Pipe rack will be plus 7 meter like this, correct? So like this, the finished levels for each facilities are identified there, correct? So this is about at what height your each facility will be there from that existing ground level. For example, suppose road level, you say road will be 300 mm above. So what you will say? Plus 300 mm, okay, from the existing ground level. So like this, the general finished levels are considered. Finished level is a level from where the either you are putting your equipment directly on that finished floor level, okay. So you are putting their equipment directly on that, correct? So that is called the finished level for making the each facility. Layout and RCC details, okay, that is basically now the construction related document. Reinforced concrete cement related plan is there, okay. Similarly, I'll go to architecture plan afterward. Foundation layouts will be there. Design calculation will be there for the foundations, correct? How deep the foundation will be there. Okay, it's is it open foundation, like a raft foundation, or the foundation here. So that is all foundation layout and foundation design calculation. Design calculation supports the type of the foundation, by the way. Then architecture plan. So architecture plan will tell you how the above ground things are coming up. Sheds, buildings, and all those things will be coming. Okay. So that is broadly about the civil. I come back to now electrical. Electrical design basis we already discussed. Then we'll be having a single line diagram. Yes, we all know that single line diagram is essential. It is nothing but a kind of P&ID for electrical. So the electrical engineer clearly knows it, from where the power is coming, what major equipments has been put into that, what is the step up, step down transformers are there, what are the how many transformers more step down levels are there, how many bus bars they have, how many loads are connected to it, air compressor, flare, instrument control room, lighting, building load, all loads are all mentioned, their different loads are mentioned, their voltage levels are mentioned. So basically this is the P&ID for electrical kind of thing. Then electrical load list calculation. Yes, this is the document to know how much load your plant is having it. And this has three different categories. You have a permanent load, which is continuously working. Then you have a standby load, something, and some off cycles. Next document is equipment cable sizing calculation. Yes, because when you are connecting air compressor and when you are cutting the main gas compressor, so main gas compressor is high load. So that decides the sizing calculations for the cable sizing calculation. You will be definitely having a big size of cable for main gas compressor and the small size of cable for air compressor. So these are the sizing calculations for the thing. And in fact, it gives also that this much core, this much square mm, this much rating will be there. All things are mentioned in that calculation. Lighting calculations, yes, it's basically how much there is an industry norm that in industrial area you have to mention at least this much lux of the light, correct? So that lighting calculation is done to achieve the number of lights in that particular area. It is throughout the plant, by the way. Okay. It's for the whole plot area of the plant. Okay. So how much lights will come where? Then earthing calculation comes. Yeah, this is one of the very critical things. Okay. Okay. So because if there is a fault, earth fault anywhere, so we are sufficiently able to do the earthing and we should not get an electrical hazard. So the earthing calculation will ensure that all the electrical equipments uh, and mechanical equipments which have electrical drives are properly having the earthing. And to make sure that earthing, we have to have earthing calculations. And there will be earthing layouts also. Okay. Then layouts, equipment, cable layouts. There will be cable routing. There will be lighting layouts, like where how the cables are routing in the plant and how the lightings are routing in the plant. So general layout for that. Then it is coming to interconnection diagram. Yes, the interconnection diagram will tell you that how you are being interconnected to instrumentation or how your two equipments are interconnected with each other. It's basically more detailed drawings of the electrical equipment and electrical interfaces with instrumentation. So that is called interconnection diagrams. Easy to identify the block. So this was about electrical. Then instrumentation drawing, instrumentation design basis, yes. Instrumentation data sheet is prepared based on the process data sheets, as I said. Then functional schematics will come. What is exact how the functions we are going to perform. from each control loops, what will be the functions, whether it is used for shutdown or it is used for normal controls like this. Functional schematics and system architecture drawings, they are driven by each interaction. Okay. And then the cause and effect diagram. Sometimes it is a part of the process, but the cause and effect diagrams are basically prepared to understand if some what will the effect, if some cause is there, what will the effect of it. And this diagram is basically is essentially required for scene study also. Okay. So safety integrity level study also, which is here because just a brief introduction to sea level explain. There are sea level 1, 2, 3, 4. So as much as number increases, they are increasing the reliability of the instrumentation system. For example, suppose if there is a high pressure, the compressor discharge line, correct? That means something has been blocked the compressor. So we have to trip the compressor immediately, otherwise it will seize the compressor. It will damage the compressor. So at that particular point of time, when we do a seal study for that condition, so in that scenario, transmitter is there or one pressure switch is there, and if that fails, only one fails, do not act at that particular point of time. So my compressor will be seized. My compressor will go under real mechanical difficult levels. It will fail, correct? So in that scenario, what they say, okay, put two pressure switches. Suppose if one fails, second will work. In some scenario, it says no, not two. Go for three and do a voting, 3 out of 2. So it trip the compressor, you trip the compressor. Okay, so this is what safety integrity studies tells you, and this does not indicate only the redundancy or the more equipment at the same location in the field. Same time, it defines the redundancy in the control systems also inside the control room, that you will be having the one input will be going to two different cards inside the PLC. If one fails, second will work. So basically, this is the concept of so cause and effect and scene study, they go hand by hand like this. Cause and effect is required for scene study. And of course, the HAZOP is completed. After HAZOP is completed, that is also an outlook for scene study construction. Layouts are general layouts, instrumentation cables and junction box where it will be there. So these are the layout in the plant. There will be the will be coming, and where the single cable will be going to each instrument from that main junction box. So that is basically a layout drawing scheme. Hookup diagrams, yes. So we'll be having the hookup diagrams for each instrument. That if the pressure transmitter is connected with half-inch connection, or a flow meter is connected with a 2-inch connection or 3-inch connection. So how it is hooked up basically to the process. So that will be the hookup drawing will be there, because looking at this hookup drawing directly, the construction engineers and the construction team, they hook up, they install the instruments basically. So this is about the instrumentation. Mechanical is a very light thing, to be very honest with you, because mechanical design basis is one developed, and then mechanical data sheet is developed. So when the compressor is arrived, for example, based on the mechanical data sheets, when compressor is arrived at site, now piping hookups is based on piping, electrical hookups as per electrical drawings, foundation is as per civil drawings, correct? Instrumentation is as per instrumentation. So basically, uh, the mechanical has a much minimum documents, of course. And some static equipment data sheets are also there, not only compressor. This mechanical data sheets includes compressors, separators, static equipment, tanks, pumps, everything. Correct? So yeah. The list of the documents what we are talking basically, a broad outlook. I'm done right now.